Hi children, today we are going to start the next topic of the chapter chemical kinetics, that is the temperature dependence of rate of a reaction. Okay, it is for most of the chemical reaction it is found that the rate of the reaction increases with increase in the temperature. For example, the decomposition of dinitrogen pentaoxide, the time taken for half of the actual amount of the material is, that is the 12 minutes at 50 degrees Celsius and 5 hours at 25 degrees Celsius and 10 days at 0 degrees Celsius. So by saying this, it is clear that the rate of almost all the chemical reaction, and here the reaction is the decomposition of dinitrogen pentaoxide, and the dinitrogen pentaoxide decomposition is carried out at different temperature, and at 50 degrees Celsius it is found that the time taken for half of the actual amount of the material is 12 minutes, that is the T half for this reaction is 12 minutes, and when the reaction is carried out at 25 degrees Celsius the time is 5 hours, the time increases, and when this decomposition is carried out at 0 degrees Celsius the time required is 10 days. It means for most of the chemical reaction the rate of the reaction increases with increase in the temperature. Okay, and in most of the cases it is also found that the rate of the reaction almost becomes double for every 10 degrees Celsius rise in the temperature, and this can also be expressed in another term, that is the temperature coefficient. The temperature coefficient and the temperature coefficient is defined as the ratio of rate constant of a reaction at two different temperature differing by the 10 degrees Celsius. So the temperature coefficient is the rate constant of a reaction, at two different temperature, and the temperatures are differ by the 10 degrees Celsius. So the temperature, the two different temperature generally selected are the 298 Kelvin and 308 Kelvin, and the 298 and 308 Kelvin are differ by the 10 degree. Okay, the rate constant and the temperature coefficient is equal to the rate constant at 308 Kelvin divided by the rate constant at 298 Kelvin. So the temperature coefficient is defined as the ratio of rate constant of a reaction at two different temperature at which are differed by the 10 degree, and the two different temperature generally selected are the 308 Kelvin and 298 Kelvin. Okay students, after that the temperature dependence of rate of a chemical reaction can be accurately explained by the Arrhenius equation. Okay, and this is first proposed by the Van 't Hoff, and after that the Swedish chemist Arrhenius provided the physical justification and interpretation. The Arrhenius give the mathematical relation between the temperature and rate constant of a chemical reaction by seeing the various observation on a number of large experiment, so that the Arrhenius equation, which consists of the relation between the temperature and the rate constant of a chemical reaction, is the K rate constant is equal to A e raised to power minus Ea by RT. Okay, this is the Arrhenius equation. Here this K is the rate constant, this K is the rate constant, and this A is named as, since this equation is given by Arrhenius, so it is named as the Arrhenius factor, or it can also be named as the pre-exponential factor, or frequency factor. Okay, this K is the rate constant, Capital A is the Arrhenius factor, or it can also be named as the pre-exponential factor or frequency factor. This EA is the activation energy. This EA is the activation energy. This R is the gas constant and T is the temperature in Kelvin scale. This is the Arrhenius equation, and this Arrhenius equation mathematically relates the temperature and the rate constant of a chemical reaction, and the Arrhenius equation is the K, the rate constant is equal to A e raised to power minus EA by RT. This A is the Arrhenius factor or pre-exponential factor, or it can also be named as the frequency factor. This EA is the activation energy and R is the gas constant and T is the temperature in Kelvin scale. Okay, after that I am going to discuss about what is the activation energy. What is activation energy? So, the activation energy, the concept of activation energy is clearly understood with the help of the chemical reaction. When a chemical reaction is taking place, the molecules of the reactant collide with each other to form the unstable intermediate, and this unstable intermediate exists for a very short time, and after that it breaks up to form the product. Okay, so the activation energy is defined as the energy which is required to form this intermediate is called as the activation energy. So in a given sample of gas, all the molecules of the gases do not contain the same quantity of energy, and also it is difficult to predict the individual behavior of the molecule with precision. So in such case, the Boltzmann and Maxwell has given a relation which describe the behavior of a large number of molecules, and according to them the distribution of kinetic energy can be described by plotting the fraction of the molecule with a given temperature, with a given kinetic energy versus kinetic energy, and this curve is named as the Maxwell-Boltzmann distribution curve. Okay, so the activation energy is actually what? The activation energy is the energy which is required by the reactant molecule so that the reactant molecule can be converted into the intermediate, so that the reactant molecule can collide with each other and they form the unstable intermediate, and this unstable intermediate is converted into the product. Okay, so the energy which is required to form this intermediate is called the activation energy, and we know that in a given sample of gas all the molecules do not carry the same quantity of energy, same quantity of the kinetic energy. So, and also it is difficult to predict the behavior of individual molecule with precision. So in such case, the Boltzmann and Maxwell use the statistics to predict the behavior of a large number of molecules, and according to them the distribution of kinetic energy can be described by plotting the fraction of molecules with a given kinetic energy versus kinetic energy. So this curve is named as the Maxwell-Boltzmann distribution curve. Okay, and the fraction of molecule is equal to Ne divided Nt. Here this Ne is the number of molecules having energy E. Okay, and this Nt is the total number of molecules, and this Ne by Nt represent the fraction of molecule with a given kinetic energy, and on this x-axis I represent the kinetic energy. So this curve is named as the Maxwell-Boltzmann distribution curve. Okay, and in this curve the peak of the curve corresponds to the most probable kinetic energy. This is named as the most probable, this is the most probable kinetic energy. Okay, and suppose this energy is named as the threshold energy barrier. This is the threshold energy barrier, and this shaded area, the molecules having energy greater than the threshold energy will react. Okay, and this area represents the molecules with this kinetic energy will not still react. Okay, so this is the Maxwell-Boltzmann distribution curve. So with the help of this curve, you can clearly understand the concept of the threshold energy barrier and how can the distribution of the kinetic energy among a large number of molecules can be predicted with the help of this curve. Okay, this energy is named as the threshold energy. The peak of this curve corresponds to the most probable kinetic energy, and it means this particular kinetic energy is possessed by maximum number of molecules. Okay, only those collisions among the reactant molecules result in the formation of product in which the molecules of the reactant having the energy equal to or greater than the certain minimum energy. The certain minimum energy is also named as the threshold energy barrier. So the molecules having the energy equal to or greater than the threshold energy barrier results in the effective collision, and this effective collision results in the formation of the product. Okay, it means this fraction of molecules means the fraction of the molecules having the energy equal to or greater than the threshold energy barrier will result in the formation of effective collision, and after that the product will be formed. But the molecules comes to this region because this region having the energy less than the threshold energy barrier. In this region the molecules having the energy less than the threshold energy barrier. So the molecules which are having the energy less than the threshold energy barrier will not react, and it does not result and it do not result in the formation of the product. Okay, it means between the reactant and product there is an energy barrier, and to form the product that energy barrier must be crossed over before the formation of the reactant, before the formation of the product. So it means the activation energy is defined as that energy which must be supplied to the reactant molecules which enable them to cross over the energy barrier, and ultimately it results in the formation of the product. Okay, so students, from this plot you clearly understand that what is the concept of the threshold energy, and the molecule having the energy equal to the threshold energy or the energy greater than the threshold energy, that molecules of the reactant will result in the effective collision. Effective collision means the collision which results in the formation of the product, and only those molecules having the energy greater than the threshold energy will react and form the product, whereas the molecules come to this side, they don't have the energy greater than or equal to the threshold energy. It means they have the energy less than the threshold energy and they will not react to form the product. It means between the reactant and product there is an energy barrier, and that energy barrier must be crossed over before the reactants are converted into the product. So after that we come on the definition of the activation energy. That is, the definition of the activation energy is the energy which must be supplied to the reactants so that the reactants must be crossed over that and converted into the product. The activation energy is represented by EA, and the activation energy is defined as the minimum extra energy which must be supplied to reactants to enable them to cross over the energy barrier between the reactants and products. So the activation energy is simply defined as the minimum extra energy which must be supplied to reactants to enable them to cross over the energy barrier between the reactants and product. And the activation energy can be simply calculated by the activation energy is equal to the threshold energy ET, the threshold energy minus the energy of the reactant. After that we come on the next point, that is what is the basic idea of activation energy and the energy barrier involved in a chemical reaction. And the idea of activation energy and the energy barrier involved in a chemical reaction can be graphically represented as, now draw a plot between here the progress of reaction on x-axis, progress of reaction, and on y-axis showing the energy. Okay, this is the energy of reactant. And initially the energy of the reactant increases till it reaches the maxima, that is the threshold energy barrier, and after that it decreases and results in the formation of product. Okay, here the product is formed and the energy corresponding to this is named as the product energy EP, and the energy corresponding to the reactant is ER, and this is the energy corresponding to this energy is named as the threshold energy barrier. Okay, so what is the activation energy? And here the transition state or the activated complex is formed. To form the activated complex or the intermediate, the reactant molecule must have a certain minimum energy, and that certain minimum energy is named as the threshold energy. So what is activation energy? The activation energy is the extra energy which must be supplied to the reactants so that the reactants must collide with each other to form the intermediate, to form the activated complex. So the difference of the energy of the reactant and the threshold energy barrier, this energy is named as the activation energy. This is the activation energy. Okay, and the difference of the energy of the reactant and the product, that particular energy is named as the enthalpy of the reaction represented by delta H, and that is the energy evolved during reaction. Hope students you understand the concept of the activation energy and the threshold energy. Threshold energy is the energy which is required by the reactant molecules to convert into the intermediate, the energy which is required by the reactant molecule so that the reactant molecules can effectively collide with each other and to form the intermediate, and the reactants does not having the threshold energy. So the extra energy which is supplied to the reactant molecules so that the reactant molecules must cross over the barrier between the reactant and product, and that barrier is the threshold energy barrier. So the energy which is required for the formation of the intermediate, for the formation of the activated complex, or for the formation of the transition state is called the activation energy. So by seeing this, it is clear that every chemical reaction has a definite value of the activation energy, and that activation energy decide the fraction of effective collision. Effective collision means the collision between the reactant molecules which results in the formation of the product. So if the activation energy for a reaction is low, the first condition is if the activation energy for a reaction is low, then what happens? If the activation energy for a reaction is low, it means the activation energy for a reaction is very less. It means this particular energy will be possessed by maximum number of molecules, and hence the value of the number of effective collision, it means the fraction of effective collision, that is small f, the fraction of effective collision, the value of f will be large, and in such case the reaction will proceed at fast rate if the activation energy for a reaction is low. Second condition is if the activation energy for a reaction is high. If the activation energy for a reaction is high, it means that particular energy will not possess by the maximum number of molecules, and hence the fraction of effective collision, that is the value of f, will be very small, and the reaction in such case will proceed at slow rate. It means for fast reaction, activation energy is low, okay, and for slow reaction the activation energy is high. If the activation energy is low, the reaction proceeds fastly, the rate of the reaction is high, and if the activation energy is high, it means the reaction will proceed at slow rate. Okay students, after that we come on the next point, that is what is the explanation of the effect of temperature. How does the temperature increases the rate of the reaction? And I have already explained you that in most of the cases it is found that the rate of the reaction almost become double by every 10 degrees Celsius rise in the temperature. So it can be understood with the help of the Maxwell-Boltzmann distribution curve. Let us consider the effect of temperature on the number of or the fraction of the effective collision. So, when we are increasing the temperature in a chemical reaction, the kinetic energy of the molecules of the reactant will also increase, because the kinetic energy is directly proportional to temperature. When we are increasing the temperature, the kinetic energy among the reactant molecules also increases, and in such case when we are increasing the temperature, the maximum of the energy distribution curve, in the case of Maxwell-Boltzmann distribution curve, the maximum of the energy distribution curve get flattened and it shift towards the higher energy value, that is it shift towards the right, because here the maximum number of molecules, the greater number of molecules having the energy that is higher energy value. So this is the Maxwell-Boltzmann distribution curve at T is equal to 298 Kelvin, and now I am going to increase the temperature by 10 degree. In such case, when we are increasing the temperature by 10 Kelvin, it means the maximum of the energy distribution curve get flattened and it shift towards the right. Get flattened and shift towards the right, because here when we are increasing the temperature by 10 degrees Celsius, the fraction of molecules having the energy equal to or greater than the threshold energy will increases. Okay, so this is the threshold energy barrier. Okay, so this is the temperature at 298 Kelvin, and this is the graph obtained at 308 Kelvin when we are increasing the temperature by 10 degree. Here the fraction of molecules, and here the kinetic energy is showing. Okay, so when we are increasing the temperature by 10 degrees Celsius, you can clearly reveal from this graph that when we are increasing the temperature by 10 degrees Celsius, the fraction of molecules having the energy equal to or greater than the threshold energy barrier almost become double. You can see that at 298 Kelvin, this is the fraction of molecules having the energy equal to or greater than the threshold energy barrier, and when we are increasing the temperature, this fraction will increase. It means the temperature increases the fraction of the molecules having the energy equal to or greater than the threshold energy barrier. So after that we come on conclusion that when we are increasing the temperature, the kinetic energy of the molecule will also increase, and this increases the number of effective collision, and when the number of effective collision will increase, which in turn increases the rate of the reaction. So in such ways the temperature increases the rate of the reaction by increasing the number of molecules with energy equal to or greater than the threshold energy barrier. Okay, after that I come to the next point, that is what is the concept of activated complex and the transition state. So next is the activated complex or it can also be named as the transition state. What is activated complex and the transition state? When a chemical reaction is taking place, certain bonds are broken and certain new bonds are formed. Okay, the bond breaking requires energy, requires the absorption of energy, whereas the formation of bonds releases some extent of the energy. This can be explained with the help of example, that when the hydrogen combine with iodine, initially it form an intermediate. This is the intermediate, and in the intermediate you can see that the bond which is present in the reactant molecule, that is the bond between H and H, starts breaking. Okay, and the bond between iodine and iodine is also start breaking, whereas the bonds between hydrogen and iodine start forming. So when a chemical reaction is taking place, certain bonds are broken down and certain new bonds are formed, and after that finally it converted into the product, and after that this is named as the activated complex. This is the activated complex or transition state, or we can say it as the intermediate. After that this intermediate is broken down and finally the product is formed, that is the bond between hydrogen and iodine is completely formed. So in this case, when one molecule of hydrogen approaches towards the one molecule of iodine, then what happens? The bond between HH and the bond between II start breaking, whereas the bond between HI start forming. Okay, the bond between hydrogen and hydrogen start breaking, the bond between iodine and iodine start breaking, whereas the new bond between hydrogen and iodine start forming. So initially, since the bond breaking predominates over the bond formation, so the energy of the system starts increasing till it reaches the maxima. This is the maxima, that is the threshold energy barrier, or it also named as the average energy barrier. So initially, since the bond breaking predominates over the bond formation, so the energy of the system starts increasing till it reaches the maxima, and after that it decreases because here the process of bond formation predominates, and since the bond formation exists by the release of energy, so the energy of the system starts decreasing, and after finally it results in the formation of product, that is hydrogen iodide is formed. Here the hydrogen plus iodine, and at this state the intermediate, that is the bond between hydrogen and hydrogen is broken down. Hydrogen iodine new bond is formed, iodine bond is broken down, and a bond between HI will be formed. So after that, this is the energy, that energy is named as the activation energy, and the difference in the energy of the reactant and product, that is named as the enthalpy of reaction, and this is the difference in the energy of reactant and the energy of product at a given constant temperature and pressure. On the x-axis, the progress of reaction. Here the reactants are converted into the intermediate, and after that finally it converted into the product. And on the y-axis I am showing the potential energy, means here I am showing the what type of changes existing in the reactants and then intermediate and then finally in the product. So initially when one molecule of hydrogen approaches to iodine, so HH-II bond start breaking, and since here the bond breaking predominates, therefore the energy of the system starts increasing till it reaches the maxima, and that maxima is the threshold energy barrier. And after that the energy of the system starts decreasing because here the bond formation process predominates, and finally it results in the formation of the product. So after that we come on what is the activated complex. The activated complex is defined as the arrangement of atoms, corresponding to the threshold energy barrier is called the activated complex. So the activated complex is the arrangement of atoms corresponding to the threshold energy barrier is called activated complex or transition state or intermediate. The arrangement of atoms corresponding to the threshold energy barrier is called the activated complex. So hope you understand the concept of the activated complex, transition state, activation energy, threshold energy barrier, what is the effective collision, and how does the temperature increases the rate of the reaction with the help of Maxwell-Boltzmann distribution curve. So with the help of this curve we can also calculate the value of activation energy, that is the activation energy is equal to the energy of the transition state, minus the energy of reactant. So the activation energy can also be calculated by subtracting the energy corresponding to the transition state. This is the transition state, this is the activated complex, okay, and this is the energy of the reactant, and this energy is the difference in the energy of reactant and product at a given constant temperature and pressure, which is also named as the enthalpy of reaction, and that particular amount of energy is evolved during the chemical reaction when the reactant is converted into the product. So in this way we can calculate the activation energy by subtracting the energy of the transition state and the energy of the reactant. So students, hope you understand these concepts. Till then, be safe.